they could tell you the amount that this spring has been compressed by. It's a compression spring, yes? So they could give you the spring constant, and they could tell you the amount that it's been compressed by, yes? Again, make sure that the spring constant in newtons per meter, and make sure that this is also in meters, yes? So what have they allowed you to do there? They've allowed you to calculate the energy stored in the spring, okay? And the energy stored in the spring is half kx squared, all right? It's in the data book. Okay, I'm not going to put numbers in, but this is the way it would work roughly, okay? So now you can work out the energy stored in the spring. Maybe it's 1.2 kilojoules, all right? Happy? They tell you the volume of the car, and they also tell you the mass of the car, yes?
Find out the velocity.
Okay, yes. So the mass of the car, maybe they tell you is 120 kilograms. So what could you do with that? Well,
Find the
you
velocity.
know the energy there, yes? Yeah? So if you wanted to, well, when that spring is released, the idea here would be all of that stored energy will become KE. So the KE will be this. But of course, if you know the KE, you automatically full house. Because if you know the KE, you can work out its speed, and of course, very importantly, if you know the KE, you can work out its momentum, if maybe it collided with something, yes? Which is not going to happen in this question at the moment yet. Happy? So we know the KE, it shoots off. Now what's going to happen? It descends here. Now, if this was a straight line down like this, we could
friction.
maybe deal with friction and angles, you know, and evaluate the friction like that. You could work out the force of friction if it was straight. Can you remember that one? The angles?
Yeah.
Yeah, is that good?
Yeah,
I don't
yeah,
know to go over it, yeah? And if you knew the distance, you could work out the heat produced. Agreed? Happy? If it was straight. Good? Yeah? I will just remind you, because you do want to revise it, if this was straight, remember how much KE it had at the top, yes? So, Nadeem? So if this is straight, you could calculate the friction, all right? Okay? But if it's curved, the exam might have to say that the average force of friction is so-and-so and the distance is so-and-so, are you me?
Yeah.
But either way, if you know the force of friction and the distance, you can multiply together to find the amount of heat produced, yes? Happy? Hamza, how would this one work if you remember rightly? You have the weight here, you remember this one, yes? You did a lot of this, the normal reaction here, you split those into the two components, yeah? You know that?
Oh, yeah.
So if it was straight, maybe they could make you find the force of friction. They could give you the distance indirectly by giving you the height and the angle, agreed? And then you could work out the heat produced. Yeah? If it was curved, they could simply say that the average force of friction is so many newtons, yes? And the distance here is so much. Either which way you can work out the heat produced, agreed?
Or they can tell us no friction.
Now, what can you do with that? Think about the situation. This is a bit of a tricky one.
You can find the velocity after.
Yes, but if the next question could be, what is the velocity at the bottom of the slope? And this is why you've got to think about the situation, Hamza, right? Okay? What's happening here? Basically, this is the physics of something falling down, right? Yeah? You could either use the equations of motion in vectors, or you can use energy. And I think in this question it's quite
Energy.
clear that it's the physics of something falling down, because they're asking you about the bottom. But I think it's quite clear that what you'd be looking at this way is going to be kinetic energy, yes? So they're asking us for the velocity at the bottom, which is essentially the kinetic energy at the bottom, right? How are we going to, there's a trick here.
mgh plus ke minus the friction.
Oh, excellent, yes. Excellent. Because what's going to be happening here, a weaker student than Omar would simply be saying there are so many ways you can go wrong. You could say we know the kinetic energy at the top, yes, and we could simply subtract the heat loss due to friction. You would be wrong. Why? Because actually there's also potential energy being released, yes?
Yeah.
If there was no friction, the kinetic energy at the bottom would simply be the K at the top plus mgh if there was no friction, yes? But in the case of friction, you'd say it's that plus that minus heat. Agreed? Yeah, are you good?
Yeah. So what's we do mgh?
So there, to find the speed at the bottom, you'd use energy, all right? You'd say that the kinetic energy at the bottom, all right, is equal to the Ke at the top. Yeah, Hamza?
Yeah.
The Ke at the bottom is going to be equal to the Ke at the top
Yes.
plus the potential energy that's being released. Yeah?
Yeah.
Minus friction, agree?
Okay.
And once you know, then you can find everything else, yeah?
Yeah.
So what have we got here? We've got the mechanics of energy stored in springs, yes? Work done, and so on and so forth, so far in this question. What's going to happen next? You wanted buoyancy, answer?
Yeah.
Well, everything's about to change because the minute it comes down to the bottom, and we now know the Ke at the bottom, and we now know the momentum at the bottom. Let me change this to make it even better, right? I'm trying to do as much as possible as revision. There's another car which is stuck in the middle of the pond, yes? And you've come down, you're hurtling down here, you're hurtling down here. Now we know the Ke at the bottom, yes? Agreed? And they say that the average force of friction, they give you the average force of friction as you go through the water, right?
Drag force.
Yes? Yeah, the average force here. They give you that to you, yes?
Times distance.
And they say that this one here, these people who are stuck, can you remember? They're stuck floating. This is at a distance of 15 meters. Happy? Agreed? So what's going to happen? Splash, agreed? And as you travel that 15 meters, you're going to slow down, yes? So when you bump into this one, you're not going to be traveling at the same speed. Then, when they bump into each other, they stick together and they move on. Agreed, yeah? Happy? Let's go. Yeah, you see the way it's working? So, nice one. So how would you work out the momentum just before it hit this one?
You find the air,
K
minus
is
the work
minus
done against
15 times
the water.
this, then Ke equals P squared over 2m. Then you,
Yeah, absolutely. You know the Ke here.
Yeah.
You subtract the heat,
The heat, yeah.
and then you reconvert to momentum, and then you
Don't-
find the momentum of this one just before it hits, yes? And these two may be of the same mass, they're identical, agreed?
Yeah.
Or not. So then what could you do? Because they stick together, what's this now? So maybe these are different, they've got different numbers of people in, yes? This one had a mass of 120, yes? This one has a mass of maybe 80, agreed? You're just about to collide. Now you know the momentum, this is when they stick together and move off as one, yes?
Conservation of
perfect-
momentum.
Yes, and it's perfectly inelastic. There's
عشان الماس بتغير في
when you
الvelocity.
move off as one, it's guaranteed heat produced, agreed, yeah? So what would you say? What would you say here? The force you could work out the momentum at the end, yes, and the kinetic energy at the end, and then you could work out, I suppose, how far it will take before they
But
finally
where's the
come to
buoyancy?
rest.
boss?
That's using equations of motion.
No, well, sorry. No, because if you knew the momentum before, you could work out the momentum afterwards,
Yes.
and you know the kinetic energy afterwards,
Oh.
and then once again you could. Or you're right. Or you could use
Yeah,
the
because
equations of motions would work. Yes, yeah,
Goes
exactly.
over the map.
Because you'd know the velocity that they move off with, and the acceleration
Is
will
the
be this
force
way, yes?
over the
And it'll be
map.
force divided by mass, yeah?
Okay, but how do you know when they stop?
Well, that'd be the question might be, how far will it travel before they come to a rest?
طيب عشان هيك.
Do you understand?
Yeah.
I could make the question like that. After the collision, how far will they then travel before they come to rest in the water? Agreed, yeah? Happy? Question mark. Now, where does buoyancy come
هي
in?
لازم ضل تستخدم 15.
Okay, where does buoyancy come in?
When it's skidding along the water.
Once they've come to rest, yes? Once they've come to rest, can you remember I said I gave you the volume of the car. Can you remember? Whole volume of the car up here. Yes? I gave it, yeah? The volume of the car. So once it comes to rest, I could ask you
Will it float or not?
what fraction of the volume of the car
Submerged.
will be submerged. But this is what you wanted, wasn't it? Buoyancy, yes? It's not difficult to answer. Okay? It's not. So obviously, when you take a car and you put it in water, it will sink, it will sink, it will sink until the buoyancy force equals the weight, and then it will stop sinking, yes? Agreed? So when it's at rest there, Hamza, what can you say? When it's finally come at rest, what can you say? Well, the buoyancy force pushing it upwards must be equal to the weight which is pushing it downwards, all right? Well, the weight pushing it downwards has been given to you,
MG.
yeah? mg. Now, the buoyancy force going upwards, yes, will be... Now, the buoyancy force only depends on what? The submerged volume, not the total volume. Can you remember? The buoyancy force was what? The density of the water times G times the submerged volume. Yes? Which is NV. Agreed? Because N is like 0.3, yeah? Agreed? Now what you know, these two forces, do you see why I put NV?
Yes.
Because it's not totally submerged. So N is the fraction that is submerged.
Okay, yeah.
So it's just sitting there, it's floating, yeah? And basically we're saying, you know, it will sink, it will sink, it will sink, it will sink until there's enough volume under the water for the buoyancy force to be equal to the weight. It will continue to sink until NV is enough to make that equal to the weight, agreed? So what equation can we write? The buoyancy force, which is the density of water known, times G known,
V and unknown.
N not known, V known is given, must equal to mg.
We cancel out the G.
And then, but everything's known, yeah? Happy?
Why'd you put the N with the buoyancy force of water?
عشان نعرف الفراكشن.
But fine, why'd you put it for the water, not with the object itself? Because you want to find the fraction of the density that's the volume that's under.
Fraction of the volume.
It's the volume of. It's the volume of the.
You do one minus right in the end.
Swimming pool. Swimming pool. Omar Masri.
It's
100 kilograms per centimeter.
1 gram.
Looking a bit thin, Omar.
My least favorite.
Sorry about that, yeah? Yes?
Yeah.
Floating,
1000.
alright?
Yeah.
If you're floating,
They equal
what
each other.
must be true?
Mg equals.
It's your weight
How's this work?
here,
One
watch
gram
your
per
weight,
second.
yes?
1 gram per meter.
Must be equal to the buoyancy force. Agreed? That's the way into the problem, right? Okay.
This doesn't make sense.
Now,
This should be 1,000 times more than this.
so
عالي ولا؟
one way of writing your weight would just be mg.
Wait, no.
Okay.
But-
Into knowing. But another way of telling you your weight is not to give you your mass, but to tell you your density. and we're all roughly got the same density as human beings, yeah?
Mm.
So instead of writing n, I could write the density of Omar times the volume, yeah? Of Omar, yeah? Happy? You're right. It's just it's so difficult for me.
No, I get it.
Because then we can speed up. Yeah, good. So that's just another way of writing your weight.
Mm.
What's the advantage of writing the weight in terms of density and volume?
You can cancel
It's
out
because the buoyancy force is also expressed in terms of density and
volume.
volume. Do you understand?
Mm.
And since they must be equal when you're floating, that's the advantage of them. Okay, let's continue. What about the buoyancy force? Well, the buoyancy force depends on not the total volume of Omar, but it just depends on the submerged volume. And
Oh,
my
that's fine,
hack
that's fine.
here is to call the submerged volume not V, but NV, where N might be 0.6, 0.4.
Good.
Okay? And so the buoyancy force, you happy?
Yeah.
The buoyancy force will be the density of water. Here we've got the density of Omar. The buoyancy force will be the density of water times G times the volume, which is NV. And these two must be equal. So the V goes with the V, the G goes with the G, yes?
Mm.
And we get left with density of water must equal.
No, relax. Density of Omar over W.
So the density of water times N, yeah?
Mm.
Agree? Yeah?
Equals
Yeah.
density.
It must equal to
Density.
the density of Omar. So the fraction that will be below water is
Density
the density of Omar compared to the density of
water.
water. Agree?
So
Happy with that?
which
Yeah?
is just 1,000.
Got it?
Mm.
So let's do some multiple choice questions on mechanics then.
Yes.
It's because
Yeah.
after the multiple choice, can we do rotation?
Yeah, please.
Yeah, definitely. So you ready?
I'm moving. It's not showing.
شو كل زي
لا اخوي مش انا بالعكس انا حمار هجيب ولا سؤال صعب.
شو كل فتح زي
We share.
ميكانكس مش هجيبه بس سهل مو سهل روتيشن سهل.
Okay, so yes, rotation. That's a good choice.
Because can we also do after we finish a few of the question bank question
عمل رجع لك سؤال صعب
Not so
you know the one
خلاص
who gave us
ما عادش في سؤال
ايش هو؟
والله لا يا اخوان
the one who gave us in the box
غير لو اني انا صح.
equation
عملت
that is x equals
1, 2, 3, 4,
إيه،
5, 6
إيه،
people
إيه،
talking.
غلط.
So 7 actually.
صراحة مش
At the
متذكر
same time.
في تي
اسكت
Should we continue? Yeah, well, just tell me about- okay, let's have a look at some multiple choice and then we'll dip and dive, yes? But the mechanics in paper 2, the first question will be a mechanics question, yes? And psychologically, that's going to be quite a difficult question, yeah? So expect it to be quite a difficult question. Yeah, it'll be the first one. People think mechanics is easy, but some of the questions are quite tricky, yeah? So don't get thrown by it. It will probably be question number 1, but don't get thrown by it, yeah? Keep your cool, you know, there's always going to be bits. It's a big paper, always bits you can do, yes? So, a person stands in an elevator. This is quite a nice one. This is, I think, zooming in, zooming out, Newton's second law, maybe. The total mass of the person in the elevator is 800 kg. So that's telling me what? That's telling me the total weight, isn't it? So they're telling me the total weight. I don't know where to really draw it because it's the weight of everything, isn't it? Yes?
Yeah.
So maybe I'll just do it like there, yes? The total weight of the system. Using G as 10, now sometimes I think in multiple choice they do, sometimes in paper 2 they use it as 9.8,
Yeah.
generally in paper 2 9.8 I think, and in paper 1 is 10 just to make answers easier. So that's so far downwards. What's the other force? There's only one other force acting on the elevator itself.
Acceleration.
And that force, there's another, it's accelerating this
F
way.
equals ma.
So there's the tension in the cable. Agreed, yes?
yeah
And if we zoom out and we're not zooming in on the man, we're zooming out and looking at the whole thing, those are the only two external forces, yeah? There are internal forces here between his feet and yeah?
Who cares about that?
Agreed?
Yes.
But if we zoom out, well, it would care, Omar, we would care if we were talking about the guy here, but I don't think we are in this question. Okay, so we know that Newton's second law, that the tension is going to have to be greater than the weight. What is the tension? This is a very easy one, isn't it?
Yeah.
So Newton's second law is that the acceleration is going to be the force, yeah? The acceleration upwards will be the overall force upwards divided by mass. And so 2 is going to be equal to T minus 8,000 divided by 800. And so 1,600
So
is going to be equal to T minus 8,000,
Okay.
and T is going to be 9,600
Which is D.
D.
kilonewtons.
Yeah.
Pretty straightforward one, that really. Could have been a lot harder. Next.
شهدين أمي.
هاد
بتكون
skip
هاد
أصلاً.
دوبل.
لا لا
Try to
لا
do mechanics. Just
بعدين- بعدين-
mechanics,
بعدين.
mechanics.
مع
please.
الدوبل.
Okay, right.
We did.
Right, but Amma's done this one.
This is
And now, okay,
skipped it. This one. Just
we're
so I
not going
can-
to skip it now.
No, just so I can do it with you. I skipped it.
Sorry?
I
Oh, you
skipped
skipped it. Okay, this is a. Omar, you have to bring an A game here, right? So I have discussed this with Amma. This is a type of question on friction that is, I think, Amma, that they are tends to be appearing
Hello.
quite a lot,
And in paper too.
and even
Yeah,
in
yes,
paper
I
too. So it's a particular. It's a particular type of question. It's a well-known type of question. Yes. Can I?
Yeah.
Yes.
Now it'd be helpful to get the question back.
Nice. This was in the specimen paper question.
Yes, there are many questions of this variety, but if everyone settles down, then I'll start trying to explain it, because you're going to need. Oh, this is a difficult one to understand, right? So, yeah, is everyone now going to listen? Because it's a typical type of question where you have one thing resting on another. And this surface here is usually frictionless, and one or the other of these two objects is usually given a pull or a push. Agreed? So, object 1, fundamentals of financial management, is object number 2. Right? Typical question. Sometimes it's as tight as it is in that one, yeah? And you give it maybe a pull or a push. If I give it a slow pull, what's going to happen? It stays together, yeah? But if I give it a very quick push, it starts moving backwards, agreed?
Yeah.
Or maybe I could push the top one. Do you get it what I'm saying? So this is a classic situation. Sometimes one's tied and the other's tied. So it's tied. So you recognize the situation, yeah? All right?
Yes.
And often they will ask about the obvious question, which is what's the maximum force I can apply often, yes? Because if my force is quite small, it stays together, isn't it? What's the maximum? If somewhere between a force which causes it to slip and not slip, there's a maximum one. And that's all to do with the static friction, exactly, yes? So this is the nature of these questions. Now, I can give you, if you listen carefully, I can give you a general way of doing these questions. Right, Sarah? It's not an algorithm. It's not going to answer every single question, but it's a general approach. So let's have a look at this question here. We can do some more if you like, okay? So a block X of weight 10 newtons is stacked on a block Y
20.
of weight 20 newtons. Block X is fixed to a wall with a light string. So that block ain't ever gonna move. Right? The coefficients of static friction between the blocks and
No, between blocks and the wall.
between the blocks and between block Y and the ground are both, so this is not smooth, agreed? So both of these are rough. Now because they've given us a coefficient of static friction, that's the maximum friction can ever be. So let's just have a little think about it. Yeah?
2 newtons.
If I don't apply very much force here, well this block isn't even going to start moving. Agreed?
Yeah.
If I slowly increase this force, there is going to become a point where this block starts to move. Agree? And all of the frictions will be the maximum value. Got it? Happy? So I'm guessing in this question that's probably what they're going to ask. Is that what they ask? What's the maximum value of F? What is the value of the minimum force F required to move block Y? Yes. Yeah? Yeah?
20 times.
Or you could say the maximum force before it starts to move, yeah? Everyone?
Yeah.
times 0.2.
Fish ولا option 20.
And what is the tension in the string? This string.
30 times
Okay, good.
Yeah.
So this is the way I do it. So they want two things. When it starts to move, yes? When block Y starts to move, they're asking for F and T. Agreed? When block Y starts to move. Happy?
Yes.
Agreed?
Yeah.
This is the way to do it. First of all, forget the horizontal forces for a moment. Okay?
Yeah.
Instead, label all of the vertical forces. Because everything vertically is easy. Everything vertically is going to be in equilibrium. Agreed? Happy?
Yeah.
With all of these stacking kind of problems, first of all, deal with all of the vertical forces. Yeah? And then we can turn our attention to the horizontal forces. After all, friction can only be found if you know the normal reaction. Do you understand?
Yeah.
So first of all, always deal with the vertical forces. A block of weight 10. So the first force is the weight of this block, yes?
Yeah.
And I'm going to have it like that, and that's 10. I don't, yeah. It's very difficult to understand when people ask these things. So, but what other force must act on block X? Because always, vertically, everything is in equilibrium, yes? So there's a normal reaction conversation going on here, agreed? I'll do that in green. So Y must be pushing X up with a force of 10. Because when you isolate X, it is at rest. But now you can chase it around because Y can't push X up with 10 without X pushing Y down with 10. Agreed? It's a
Action
conversation.
reaction.
Yeah. Now we zoom in on Y. Y is also at rest. Agreed?
Yeah.
Or are we not accelerating up or down? So far, what's the weight of Y?
20.
No, block X, block Y, they're both, block Y is 20, thank you very much. So I'll do this in another colour, yes? So we've also got the weight, which is 20. Now we zoom in on Y. What have you got? 20 and
30.
10, which is 30. So the normal reaction force here, pushing upwards, must be what?
30.
Must be 30. Therefore, this one pushes the floor down with 30. Agreed? Happy? You just deal with starting at the top. You work down. Yeah.
Okay.
Happy? Always do that with all of these stacking kind of questions. So over here, over here, what are we doing? My approach in this problem would be to do start at the top, yes. You work them up. Well, I'm going to go home in a minute if people aren't. You wanted to revise. It really is coming to a point where I think go home and revise yourselves where you don't distract each other. This is where it's a fine core, isn't it? You know what I mean? You'd probably be achieving more at the moment if you were at home, not distracting each other, than you would be if you're here. And I think we're getting to that point. So you're happy so far? These aren't easy questions, yeah?
Yeah.
We've got everything? Now we can deal with what? Now we can deal with horizontal forces, and this is where it gets tricky. Okay? There's definitely going to be a force here, which is what? T. Friction is the tricky one now, yes? But X is remaining what? Stationary. There's a force of friction, isn't it? Between X and Y, yeah?
Yeah.
So, the tension this way, which way, the trick here is which way is the frictional force acting?
With it.
Well, it must be acting this way. Because this is at rest, always at rest. If the tension is acting that way, the frictional force must be acting this way, agreed? Happy? And the size of that frictional force
Must be equal.
is going to be 0.2 of the normal reaction, which is 2 newtons. Agreed? Happy? So we know that there must be a frictional force here, this way, of 2 newtons. But friction is an action and reaction pair. So as long as you know that the friction on one is this way, the friction on the other one must be the other way, because friction is an action and reaction pair. Do you understand? So the secret here is to find out guaranteed one of the frictions, and you also know now on why the frictional force must be that direction, yes? Agreed? But they say, what is the maximum? So what's the frictional force here? There's another frictional force acting on Y, isn't there? There's a frictional force at the top, and there's also a frictional force at the bottom. Agreed? Yeah. Happy? But which way is that? Which way is Y trying to move? This way. And so the frictional force at the bottom must be this way, agreed? Happy?
Yeah.
And it must also be 0.2 of the normal reaction
Of
force.
30.
And the normal reaction force was 30.
Which is 6.
0 point is 6. You get it? And they're talking about the maximum where it just stays the same, yes? So now we can answer our question, I think. Can we?
Yeah.
Yeah.
Yeah, we can.
You
If we zoom in on X, then T must be equal to 2. And if we zoom in on this one, F must be equal to 8. Yeah? And that answer's there. Is there another one? Can you
What's
pull
the
up
answer?
But
why do we add the friction on the top and the friction on the bottom to Y?
Because Y is experiencing 2 forces of friction. There's a friction between. I'll show you here. All right. This is Y. Agree? And this is X. Yes. If you push this one across here and this one across there, how many forces is this experiencing? There's a force of friction between this and the bottom. Remember, this is being held with a string. So there's also a force of friction here. Do you understand? This book is experiencing a force of friction here and a force of friction there.
Default.
I mean,
You get it?
Yeah.
Yeah?
تنين.
Agreed?
Okay.
Next one. Okay, these are quite good. I've shown you an algorithm. What is my algorithm? It's simply do all of the vertical ones first, yes, and then go horizontal. And the trick horizontally is to find one is the direction of the force of friction. Agreed? Find one that's obviously that way, and then it's an action direction. Let's go. Shall we? So a book of mass little m lies on top of a table of mass big M that rolls freely along the ground. So there's no friction here at all, yes? Zero friction, yeah? Happy? Got it? Nothing. The coefficient of friction between the book and the table is mu. Yeah? Agree? A person is pushing the rolling table. So here is our force, yes? Okay, Emerson? Now there's no friction here, agree? So if we zoom out and look at the whole system, Emerson, we have a whole system whose mass is big M and little m, and there's only one external force. This is no friction, agreed? So this system is guaranteed to what? Accelerate. Do you understand? No friction here, right? Take the whole thing, an external force. So this whole thing is going to what? Or more accurately, big M, which is being pushed, is guaranteed to accelerate. But there's the question. You see where the question is going to come. If big M accelerates too much, what's going to happen to little m? It's going to relatively, it will move backwards, isn't it? Yes. But if this acceleration is quite slight, then they will accelerate together. Do you understand? Yeah. Of course, it's obvious. Unless you've not lived at all. Agreed? Yeah. Yeah. So what happens really all depends on the size of that force. Agreed? Yeah. If this acceleration of big M is very, very quick, then the inertia of little m will mean that it tends to stay where it is and it will slide backwards, agreed? But if this force is small enough, then they could both accelerate together. Yeah?
Yeah.
Got it? I mean, you just have to lift a little. Yes, sir? Yeah?
Yeah.
Okay, so what's the question? What is the maximum acceleration of the table so that the block does not slide backwards? So what's the maximum possible force so that everything moves off
3.
together, yeah? Happy? Yeah. Well, maximum is going to use static friction, agreed? So can we do it my way again? It's an algorithm.
Yeah.
So first of all, let's forget about this, isn't it? We're going to need to know frictional forces and stuff like that. But let's just do this first of all, vertically, yes? And always start at the top, I suppose. So what two forces are acting on this one? Gravity, which is little mg, and vertically there's the normal contact force, which must also be what? Little mg. Now we go here, yeah? That can't push that one up. This one is being pushed down with little mg. Plus, this one also
Big
has a weight, which is big mg. And if we need, there's going to be a normal reaction here, agreed? Yes?
Yeah.
But I don't think
We don't need
we're
it.
going to need it.
No
But we
friction.
could put it there, yes? Let's include it. It's not difficult. Because what's the
MG
total
plus
weight
MG.
of the system pushing down?
M plus N.
The total weight is big mg plus little mg. So the normal reaction, yeah, happening here together, the normal reaction must be equal to big mg plus little mg. I don't think we're going to need that there. Happy? That's stage one. Now, what are we going to do? We're going to do stage two. Stage two involves putting in the frictional forces, yes? The horizontal forces. You get it? It's algorithmic. So, where would you start? I think we'll start on the top one, yes?
Yeah.
The thing about the frictional forces here is you've got to find which way it wants to move. Agree? So, which way is this one trying to move? Careful, careful. Which way relative to the trolley?
There.
Which
To the-
yes, relative to the trolley, this one's going to want to try to move this way. And so the force of friction is this way. You could equally as well have looked at this one, right? Which way is the force of friction going to act on? Oh, I think I've got it wrong, haven't I? I've got it wrong. Because if we think about this trolley, yes? Yeah? Which way is this trolley trying to move? Definitely, this trolley is
The
trying to
right.
move this way, yes? That's undeniable, agreed? Yes? Undeniable. It's being pushed, agreed? If it's trying to move this way, then the force of friction on it must be that way. So I made a mistake. Do you see what I'm saying? Go for which one is obvious. And I think it's absolutely obvious here that this trolley, well, we know it's trying to move this way, yes? You couldn't possibly have a situation where friction helps it. Agreed? So therefore this force of friction must be what? Must be the other way, yes? And what's the force of friction going to be? It's going to be mu times little mg. This one is going to be mu times little mg. And now we're in a position. Agreed, yes? Remember these mu's are static friction, the maximum possible, yes? And what's the question saying? Which is, what's the maximum acceleration of the table? What's the maximum acceleration of the table, yes? Yeah?
Mu mg over.
Well, what's acceleration? Acceleration is equal to force divided by mass. We've got everything now. The acceleration of the table, agreed? Yes?
It has to be
The acceleration of the table. What's the overall force acting on the table?
force
Is going to be F
minus
It's not in
It's a vast paper.
Ah,
High vast paper.
Ah, yes.
Oh, I remember now.
so Chris, there have to be mass m. The maximum acceleration is the acceleration of the block on the top of the book.
Is that what they're looking at?
They want the maximum acceleration of the table.
Oh, so the book does
So that
not
doesn't
slide
move
backwards
backwards.
relative to the table.
So that they have to be moving same acceleration.
Okay, yeah, the acceleration has to be the same, yeah?
So you can just equate the acceleration of the table with the book.
Or find the acceleration of the book, nothing's changing.
Oh, so yeah. So this is a slightly tricky one. What's the, so I was getting sucked in from using the second law here. But what is the maximum acceleration of the table so that the book does not slide, yes? But if the book does not slide, then everything has the same acceleration, agreed?
Yes.
Yes? If the book does not slide, what can I say? The acceleration of this one must equal to the acceleration of that one. Do you know where I was getting nowhere? Do you see why I stalled? Because I was saying they want the maximum acceleration. I was zoomed in on the table, yes? And I was going, acceleration is force divided by mass. And then, do you see why I stalled? Because I don't know this force. So the overall force on the table would be F minus mu mg over big M. But I don't know F. Do you see what I'm saying?
Yeah.
So that's why I suddenly saw that that's not going to get me anyone, yeah? So the way into this one is that if they stay together, then the acceleration of this one and the acceleration of the table must be the same. So the acceleration of this one, zoom in, the acceleration of this one is going to be equal to mu mg over m, and that must equal to the acceleration of
The small block. Yes, the small block.
this table.
We're gonna have
Yeah,
the
but
same
that's
acceleration.
Yeah.
So yeah, that's what Mr. Christian basically solved it. Just mu mg over m, so the m's cancel out.
Oh, sorry. Yeah, I've done
This
this
is the
every
same
time I
exact-
do this question, isn't it? I've already got the answer.
Yeah.
I've already got the answer. Yes.
Yes.
The answer is there because So the way into this one actually was not using Newton's second law, but it was just saying.
شيء الجواب.
Mr. Chris, you had the same problem last time. when you were
I did
following.
exactly the same.
Yeah.
I have a mind block on that one. Okay, one more. One more because it could appear in paper two as well. Yeah?
عملناه وحكى لنا
I'm getting fed up. Okay, so one more here. I'll wait for everyone to sit down. Because, I don't know, I'm glad everyone's so confident they don't have to listen to these. You're all going to get them right when they turn up in 4 days' time. Whatever it is. So,
Just 14.
okay. So, there's no point. No, it really is getting to this has got to be the last one because it is getting to a diminishing, you know what I mean? Because what's happening here is this, you're all distracting each other. You would be learning better if you were at home on your own. Definitely, I think, undeniably. So, a block of mass 2 kilograms is placed on a trolley of mass 5 kilograms moving horizontally. Force of 8 newtons is applied to the block, which slides on the surface of the trolley. Free to slide, yes? The frictional force between the trolley and the ground is 0, yes? Happy?
Yeah.
Okay, so where's the force being applied to? The top one, yes? So, but you need to think your way through this system. What would happen? There's no friction here at all, right? There is friction here, agree? If that force is very, very high, what's going to happen? It's going to slide. But if that force is not very high, then it's going to take the trolley with it. Do you understand? Yeah? Happy? And so the trolley it says the trolley is accelerating. So the trolley, we mean the bottom one, yes? The bottom one is accelerating at a rate of 1 meter per second every second. So there must be a net force. And this is going to be quite easy. This is quite an easy one. Yes? I don't know. What's the question? What's the coefficient of dynamic friction? All right, let's go. Let's go. Force is acting on the top one. Help me out. What's going down here? Do they say?
Yes, mass of the block 2 kg.
What's the mass of the block?
2 kg.
So this is 20. Normal reaction force here. This must also be 20, yeah? This is an equilibrium. This one here must be 20. Action, reaction, yes. The weight of this trolley is 50. Agreed? So gone over there for 50. And that's the end of the story. This is frictionless here, yeah? Happy? And what do they tell you? The trolley, which is the bottom one, yes?
Sorry.
Sorry, friction now, isn't it? Oh. If I'll have to do it again. Honestly, how many of these sessions have I done? With every single day, apart from
Sunday.
one Sunday. So I've done 10 of these, like 20 hours. Honestly, if I turn around once more and no one's listening, then that's it. Everyone can, because I'm through. Yeah, you know what I mean. I'm trying to do everyone a favour, but no one is focusing. How are you going to get through paper 2 physics if you can't focus? I don't know. Sarah, do you want to do it?
No.
Why? You can do it.
I can't do it.
Sorry? That's my point. You can't get out of it because either you can't do it, in which case you should have been listening.
I've already answered this question.
Option A. Oh, you've done it already in revision.
Yeah.
Okay, I got it. Okay, so you already know the question, but that the correct way with respect to me, if you already know the question, is just to sit there being quiet, right? Rather than to distract, isn't it?
Yeah.
Or is that just old-fashioned? Okay, so
What is the friction?
we're onto friction, isn't it? this is, I think, the tricky one. But one of these two friction, there's friction here, but this is the tricky thing. You always got to decide which one's obvious. Which, the direction is the problem, isn't it, yeah?
Mm.
But which one's direction is obvious? Well, I think it's the top one, right? Because the top one's got the force being applied to it. The top one is definitely wanting to go that way.
Mm.
You see, you nail the one whose direction is guaranteed. So here, you know, the friction here must be this way, and it's going to be equal to 20 mu, yeah? Then, of course, the friction here must be this way, and equal to 20 mu, yeah? Finally, what is the acceleration, what is the value of mu? Well, they've told us the acceleration of the trolley, yes, is 1. So we zoom in on the trolley, and we use Newton's second law. 1 equals the net force on this one,
Which
is
just
going to
20
be
mu.
just 20 mu divided by its mass, which
Five.
was 5. So you're going to get
Five
mu
over
is
20.
equal to 1 over 4. Yeah, when you solve it, yeah?
Yeah.
Because 20 mu is going to be equal to 5, mu is going to be equal to 5, yeah. So that's actually quite an easy one, yeah? But the process for all of them has been exactly the same, yeah? Go through vertically. I always think that the trickiest one is the friction, yeah?
Mm.
But one of the direction is the direction of the friction. But one of the directions will usually be obvious, especially if there's a force, an external force being applied, yeah? And then once you've got that, everything really comes out in the wash, yeah? Yeah? Happy?
Yeah.
That's the principle. But you can see why you do the vertical first, because you're going to need the normal reactions to find out the
Friction.
friction. Did you get it? Happy? Yeah.
Can we do one of your rotational questions? Like,
Yes. If you want to do rotational, yeah?
Yes, please.
You want me to make up a rotational question, something, yeah?
because the multiple choices aren't that.
Not that tricky. Okay, so rotation, I think that's a good one, right?
There's
Rotational
this
physics. Okay, this one? Is this rotational or not? It looks like rotational. We can make it into a rotational question, yes? It's classic.
Actually, it's tethered object.
Hmm?
It's tethered object.
It's a tethered object question, but we could make it into a rotational question,
Okay.
yes?
Yeah.
Actually, this would be a little bit difficult if it was a rotational, but this is actually just a tethered object, I think, because it says what? Frictionless pulley of negligible mass. All right, Sarah? So this is just a good old-fashioned tethered object. You remember how that works? You can zoom in on this one, apply Newton's second law, zoom in on that one, apply, or you can stick them together. Yeah? Yes?
Mm-hmm.
Good?
Yeah.
But let's take that one as a way into usually in rotational physics there are 3 different categories of questions, right? There's a category of questions on Sarah on conservation of momentum, yes? There's a category of questions on buckets and pulleys, yeah? And I think we'll do that one first, yeah? Okay? So let's make up a question. I'll try to make up a question that tests as many things as possible. I'd like to go over to what are the equations in your data book? They're all there. Can you remember? Do you want? Yeah. Every analog has. So basically, let's do some very very basic revision. If you've got a we'll go straight into a question. Oh no, if you've got an axle here, yes, and a single point of mass n. And radius what? Going around in a circle, yes? Happy? Yeah? The moment of inertia of a single point rotating, yes, of a single point rotating about an axle, yes? Remember I did that vertical, with a mass going around. Yeah, it's a good one.
Yeah.
The moment of how difficult is it to accelerate something like a mass in a vertical circle, yeah? How reluctant is it to accelerate angularly? You're right. Of a single point is mr squared. Agreed? What about a bicycle rim? Well, a bicycle rim is just a whole load
sum
of single
all r
points.
squared.
So it will simply now be equal to mr squared. Yeah, where m is the total mass. Agreed?
Yeah.
Yeah. What about this is on the mock I wrote. Can you remember? What about a disk? So here we have in blue a ring of radius r and a mass m, and here we have a disk of the same radius and the same mass.
So mass is concentrated.
Do you understand?
on the rim.
A rim of mass m and radius r, and a disk of the same mass, the same radius. Which one's going to be harder to accelerate? Which one's going to be the hardest to accelerate?
The one with
Which
the
one's going to
mass-
have the most inertia?
The mass concentrated at the
The
radius.
bicycle wheel, yes? Because the further away the mass is from the axis about which it's rotating, the harder it is to get it to you. Agreed?
Mm.
So this disk will have maybe a fraction of that. Actually, it's equal to I is equal to mr squared over 2. Do you get what I'm saying? Yes?
Yes.
Yes.
This is the basic, okay? So a system has a reluctance to spin, yes? A single point, like a bucket, I could even do it down here, but yeah, I could get. It's going to be very dangerous. So supposing I put a 1 kilogram mass on tied it on there, yes? Which I have got here
Just
somewhere.
try the scissors.
You have the ball.
I won't, that's
The
be too
scissors.
dangerous, right?
The
A 1
scissors.
kilogram mass there, and I simply take a 1 kilogram mass and I get it to go around in a circle, yes? And I want to try to give it angular acceleration. Well, what is its reluctance? Its reluctance to accelerate. That's just given by mr squared, yes? Okay? The further away it is, yes?
Mm.
The harder it is to get it to accelerate. If it's very, very close, it's easy, yeah? Okay? Yeah? Is everyone good with
Yes.
that?
Yeah.
Then you have all the analogues, yes? Angular momentum. What's angular momentum going to be equal to? Angular momentum. And we have omega now, isn't it? The speed, which used to be meters per second, is now omega. It's radians per second, yes? Yeah? The momentum, which used to be kilograms times mass times velocity, yes? Now the angular momentum, which they give L, I think, in the data book. The angular momentum is equal to the moment of inertia times, yes? The angular speed. What about distance? Okay. Anyway, these ones you know, and the equations of motion. You remember? The equations of motion used to be like S would be the linear distance, but in angular physics, it's the total angle you turn. Yes. Agreed? Yes. Yeah. Happy. Anyway, I'll bring those all together right now for you. Okay.
Yeah.
So let's do one which tries to bring everything together, and then we'll do one on angular momentum as well. So this is a classic one. You have a pulley. I showed it to you up there, yes?
Yeah.
Agreed, guys? But it's a pulley. I'm going to try to make this as hard as possible. So viewed from the side, it's a pulley on a pulley. Do you kind of understand? This is the wheel.
Yeah.
Does it? Do you understand my diagram?
Like the one.
So this is the actual pulley wheel itself, all right? Okay, that's the actual pulley wheel itself. But coming out of here, soft.
That's a highlighter.
There's. Do you get what I'm saying? It's like a cork on a disc. Yes.
Yeah.
I hope you can understand.
Yeah.
So we'll do it both ways. So wrapped around here, on this one, wrapped around here is a rope, yeah?
Yeah.
And down here, we've got a mass, and we've got an angel holding it, yes? And this is the floor. Got it? And this height might be given. This is a very good example because everything's here, yes? Yeah?
Yeah.
Happy?
Yeah.
They'll give you the mass of the big disk is given, say 0.2 kilograms, and the radius of the big disk is given, maybe 30 centimeters. Yeah?
Yeah.
Happy?
Mm.
Now, the mass of this bit is given to you, 0.05 kilograms, and the radius here is given to you, 0.02 meters. Do you understand? Yes? Good?
They give you
Yeah.
the inertia too.
Okay, well you don't need it. But the moment of inertia of a cylinder about its axis is mr squared over 2. Happy?
Yeah.
Well, the obvious question is, and it rotates about this axis. So the obvious question ultimately is what's going to happen when the angel lets go, yes? Well, this one is going to undergo linear acceleration, hopefully. Yes?
Yeah.
Let's make this suitably big so that it will do. Let's make this one a mass of 5 kilograms, yeah? Okay? So this is going to undergo linear acceleration, and we could use the linear equations of motion, yes? S equals ut. This one's going to undergo angular acceleration, and we could use the rather than talking about the linear distance and the linear speed, we could talk about the total angle it turns, yeah? Remember? What are the angular formulas? Omega F V equals U plus, yeah? Do you understand? All of our equations of motion, V equals U, and S equals UT, yeah?
Yes.
What's S? That's going to be theta equals
Omega T.
omega. Do you understand, yeah? So everything's going to be, where we had distance in meters, now we have the total angle, yeah?
Yeah.
Where we had linear acceleration, everything's there in your data book. Happy?
Yeah.
So, what could you ask? Well, when I suppose one question we could ask ourselves is when the angel lets go, tick tock, tick tock. Should we ask ourselves how long it will take? Yes.
Yeah.
What will its speed be? Agreed. Now, if the pulley had 0 mass, it would just be a straightforward application of mechanics, wouldn't it? We could say P becomes K, yeah? We could say speed at the bottom, it would be falling freely.
There's an inertia.
Yeah, but now it's not going to be that simple. So what are we going to do?
Find A.
Okay, really what we want to do is we want to find A, yes? So let's do it from a scalar point of view. Okay, so
A is equal to T minus
this is quite tricky.
50 over.
Maybe I should have made this a little bit easier.
We
بس
can
you
do
need to
two
add-
equations.
اه لازم نزيد الام والار والام والار.
No, I'm going to keep it as it is.
We can do
because
two
it's hard,
equations.
yes? So what have we got up here? Tension.
Tension.
And what have we got here?
Tension.
Tension. And what have we got down here? We've got 50, yeah? 50 newtons, okay? So what we're going to do, because really I can't predict the future unless I know the acceleration, agreed? Yeah? So what I'm going to do is I'm going to zoom in on this one and find the acceleration, which is good old-fashioned linear acceleration, to get one equation, right? So if I zoom in on here, what am I going to get? The linear acceleration downwards equals
mg minus
50 minus t divided by 5. Agreed? Yeah? That's equation number 1. I can now zoom in on the pulley, right? And I want to try and find the angular acceleration of the pulley. So I apply Newton's second law, yeah? Happy? The angular acceleration
Torque over inertia.
is going to be, thank you very much, torque divided by the total inertia. Okay? what's the torque?
T times
The
R.
torque is T
Times small r.
times little r, agreed?
Yeah.
Yes.
So the torque is 0.02 T, but the inertia has to be the
Both of them.
total angular inertia, agreed? So I have to say the angular inertia of this one and this one together. Okay? So underneath we're going to have the half is common. So we're going to have half. This one has got a mass of 0.05 times
0.02 squared.
0.02 squared plus this one has a mass of
0.2.
0.2 times
0.3 meters.
0.3 squared, yeah?
Yeah.
Now, the point is that let's just, we don't have a calculator here, but the point is at this stage, we can solve this one. The angular acceleration, alright guys? We have a calculator, agreed? So let's just make up some numbers. The angular acceleration is 0.2 t. Let's suppose in the bottom comes out to be
Mr. Chris, it's 0.009.
0.009.
No, the acceleration is 0.009.
That really doesn't help me.
Yeah, the تحت 0.2 t over 0.0. Okay.
I'm doing it one way and you're giving me an answer for something completely different.
No, I told you what's the thing done.
عندك two unknowns.
All of this.
والله.
All of
Only
this.
تحت.
Oh, he's saying he got the
The
inertia.
denominator. The denominator.
This on the bottom.
Yeah.
Okay, that's what I wanted.
Yeah.
Yeah. So you called that the angular acceleration. Oh, good. Good. It's 0.01. 0.09, yeah?
Yeah.
Yeah, thanks, Mom. Yeah, that's exactly what I wanted. You just gave it the wrong name. That's and so we've ended up with what? Now is the thing. We've ended up with what? Two equations, but they've both got what? A tension in it, and they're different accelerations.
Times
So what's my next approach?
So we make
Well,
them
really, I
same.
want the linear acceleration. So I'm going. What are we going to say here? The linear acceleration
over
is the
R.
angular acceleration times
R.
by r. Yes.
So A over R.
Yes. So this one I
العكس
can
هو
write
بده إيه
as
over. هو بده إيه.
a over
لا.
now I can see where there's going to be a little bit of a problem because which r am I going to use?
Mr. Chris, what did you do here? 2 equals
مش 2 high by angular acceleration.
Okay,
Small one, no?
So angular acceleration.
Yeah.
It's like accelerating, but
Yeah.
Yes. So little r. Yes. So a over 0.02 equals 0.2 t over this, and now what you do? Now you just eliminate t to get a value for a. Now that's a in what? That's a in meters per second every second. So now you could just use
Equation.
linear equations. However, to find the time, agreed?
Yes.
Happy? Got it? So supposing the time now is let's say the time is 0.7 seconds, agreed? What could I then do? I could say by the time it hits the floor, how many revolutions
Ooh.
does the system turn? Agreed? Do you get it? In that time, how, not the distance travelled, but the total angle
You can find
turn.
theta and
You just
theta.
use the equations of
Easy.
motion for this
Easy.
one, isn't it? Yes?
So
So what's the initial angular speed? Which equation of motion would we use here?
I mean, I'm just I'm up in bad.
You'd use delta theta
just the
equals.
acceleration is 15. If you want.
No, I don't.
what's the equation of motion? Delta theta equals.
Oh. Can I, look, I don't, is everyone, we could do this if we wanted to, agreed?
Yeah.
Let us not waste time doing it. Is everyone happy you could
Yes.
find A, yes?
Point received, yeah.
And if you could find A, you can find the time, agreed?
Mhm.
Well, the next question is, let's go up here. In that time, what's the total angle turn?
For the small one.
Well, for the system, they're stuck together. Yes? What's the total angle term?
UT
Agreed?
plus half.
Delta theta.
Well, you could say for the bottom one if you like. But the point I'm trying to make is what you now use. You now use the equations of motion, but not linear. What's the linear distance is s. And what equation did you use? You used
UT
s
plus half
equals
AT.
ut plus half at squared. Well, in angular physics, it's not the total distance
The theta.
traveled, it's the total angle.
It's the total change of
So what equation are we going to use here? It's in your
Theta.
data book.
delta theta.
Theta, the angle,
Equals
yes,
omega
equals
c,
ut. It's going to be in your data book as
omega
omega I times t plus half
Angular acceleration
Yeah,
t squared.
alpha times
T squared.
t squared. Agreed, yes?
Yeah.
So in that time,
You have
how
it
many revolutions did it take? Well, what was the initial angular speed? 0. And so now you just go half times the angular acceleration
Which we have,
that you have.
and t
Times
which we
the
have.
t, yes?
Yeah.
I could also have said, what is the angular momentum of the pulley as it hits the bottom? Well, the angular momentum is easy, right?
Yeah.
Now you've found the angular speed.
Just
Oh, no, if I said, what is the angular momentum of that pulley when this one hits the bottom? Well, to find the angular momentum, you're going to need to know I and omega. So really, you'd have to work out, in the first question it said, how many rotations does it take?
Mm.
Second question is, what will be its angular speed
You have
when this
the-
one hits the bottom, yes?
Yeah.
So now you'd use not v equals u plus at, but you use the angular speed at the end equals the angular speed at the beginning, yes?
which is 0.
Plus alpha times t with, that was 0, yeah?
Yeah.
To find out the angular speed, and then once you've got the angular speed, you can find out its angular momentum. Happy?
Yeah.
Yes.
So that's the kind of first type of question. The second,
Sorry, but is t in the rotation the same as the time taken for the
Oh, yeah, but
Yeah,
what's
of
the
course.
time?
the other type of questions they often ask are on conservation of momentum. Yes, yeah, conservation of momentum. So let's just do that one this way. So supposing you have a disk, yeah. I think they use spaceships very commonly. Yes, yeah. So they have a space station here, yeah, and the space station is spinning around its axis to create artificial gravity. Okay, happy? And they give you the radius of the space station, and yeah, and it's a solid space station like that, yeah, spinning around, and they give you everything like that. And in this situation, what could happen is that they could say that another spaceship, yeah, arrives and docks, yeah, by landing on the spinning disc, yeah? So you've got a spinning disc and something just drops on it. Agreed? So what's at play? This is going to be conservation of what? Conservation of momentum, yes? Because obviously if you've got a spinning disc and something just drops on it and it's going to slow down, isn't it? Yeah? So it's conservation of angular momentum. What would you do? You'd say the angular momentum of the first disc, yes? The angular momentum before must be the angular momentum afterwards, okay?
True.
And they'll give you the moment of inertia of this disc, and they'll give you that mass. Okay, well, let me try to put some numbers in here. Okay, so let's do before and after, right? Because this, I'm sure they're going to ask conservation of angular momentum. Here goes. There's our space station, right? This is before. Okay? Yeah? Agreed? And a spaceship of known mass, 2,000 kilograms, yes? Is descending. Yeah? Got it? Like this. And it's going to descend and land on there, yeah? Descending vertically. Meanwhile, your space station is rotating, yeah? And they tell you the mass of the space station, something like 2 times 10 to the power 8 kilograms, and the radius here. Agreed, yes? Happy? and they tell you the angular speed. Yeah, happy? Yeah.
Yeah.
12 radians per second, isn't it? So because it's just merrily rotating, yes?
Yeah.
And this is landing. Okay? It's in space. So that afterwards, what happens? Afterwards, our rocket docks on there like that, yes? And of course, the thing is still what? It's still spinning. But clearly, its angular frequency is now, its angular speed is now going to be less, right? Obviously. But what is this asking about? It's asking about conservation of angular momentum. So what would you say here? You'd say the total angular momentum before must equal the total angular momentum afterwards. Well, there's only one thing that has angular momentum before, and that's the space station. Agree?
Yeah.
Yes? So momentum is mass times velocity. Angular momentum is I times omega. They've given you omega, and you can work out I as mr squared over 2. Agreed? So you can work out the angular momentum of this before. Happy? Afterwards, okay, you have one object, before you have one object. So the angular momentum afterwards must be the same as the angular momentum before, yes?
You add the.
So we know the angular momentum before, that's done, that's known, big red tick. So the angular momentum before must be the same as the angular momentum afterwards. But what's the total angular momentum afterwards? The rule here is that because the rocket and the spaceship are all rotating about the same axis,
You have to add.
you
both
can
of
simply
them.
add the two angular momentum together. Agreed? And actually, you can do a little bit better than that
Inertia.
because they've both got what? I mean, the rocket's stuck on the. So they're both rotating with the same what? They're both rotating with the same omega, yes? So angular momentum is what? Omega times I.
But how are they
So the-
rotating the same?
Because the rocket has landed on
That's
this
the
one.
idea.
So the angular
Yeah, but it becomes slower because the mass is.
I mean, it's not
the
compared.
angular velocity is the same.
Yeah, okay.
So what's the total angular momentum afterwards? It's going to be omega because they both share that times the moment of inertia of that plus the moment of inertia
Of the
of
whole thing.
that. Do
I
you
plus-
understand?
Yeah.
The moment of inertia of this we already know, and the moment of inertia of that we can
The mass times
calculate.
the small radius.
Careful,
more squared.
careful. The moment of inertia of this disk is mr squared over 2, but the moment of inertia of the rocket is like a single particle,
More
isn't it?
squared.
So you'd be expected to know that you could treat that as mr squared. Agreed?
I
Yes.
have a multiple choice on this.
Yes. Okay.
Do you want it?
Are you all good with that?
Yes.
So it's just angular conservation of angular momentum. But I want to show. Yeah.
Do you want it?
Okay.
Yes. It is happening.
Have you got a?
It is delay on
I'm going to make this the last one then because it's 12.
So Chris, when do you start revision sessions grade 11?
من هلا.
There's one on Saturday.
They've got a test.
Tomorrow.
Yes, they've got a test on Wednesday.
Yeah,
So
my sister is.
yeah, you've got a test on Wednesday. So I'm going to do it tomorrow.
Whoa.
And the rest of the week. Okay, so let's have a look at this one, then we'll quit yeah?
Yes.
So turntable of mass m. Oh, good one. It's what we were just talking about. Turntable of mass m and radius r spins freely about the vertical axis at an angular velocity of omega. The moment of inertia of the turntable about the axis of rotation is half mr squared, yeah, for a disk. A small body of mass m, this is very easy, right? A small body of mass m is dropped close to the edge of the turntable with negligible initial velocity, yes? So this is going to be what? This is conservation of momentum, yes? I mean, yeah, got it? So what's the question? The body comes to rest relative to the turntable, it stays on the turntable, yeah? What's the final angular velocity of the turntable? Let's do it. Angular momentum before was I angular momentum before was the moment of inertia of the table was half big M big R squared multiplied by omega. And that must be equal to the angular momentum afterwards. Now, so that's omega, yeah? But now we're going to have a new omega.
Omega I and omega F.
Yeah, so that's omega I, yeah?
Yeah.
And angular momentum before must be equal to angular momentum afterwards. They're both going around the same axis, yeah?
Mm.
So we could say I of this times omega plus I of that, yes? Okay, let's do it. So I of the disk is going to be half m r squared times omega f, yes? Plus that point, which is just, well done, which is little m squared r, also omega f, yeah?
M R squared. مش M squared.
Yes, thank you. Thank you. Yeah. I was just making a deliberate mistake.
To make
Okay,
sure if you're awake.
so-
easy.
Okay, let's be a little bit careful with the ends,
You can
yes?
cancel out
Yeah.
the R.
This is a big M, and this is a
Big M.
big N. Well, the answer's going to be there somewhere, right? But let's just tidy this one up by saying,
Cancel.
what we're saying, half,
Cancel the R's.
no.
Because that's on or.
No, yes, yes,
Yeah, because
yes.
put it
Because
at
the
the
R's
end.
are all the same, yes?
Yeah.
You're right. Well spotted out. So we can
Good
actually
spot,
cancel the well spotted, yeah. So that takes us to where? That takes us to half times big M times omega, which they just called omega, equals half times big M
WF.
plus little m times
WF.
WF, and therefore WF is omega F is going to be it's there somewhere, isn't it?
2,
It's there.
4.
It's
No,
8.
no,
It's B, it's B.
It's A. It's A because omega F is going to be equal to
Half.
Half. big M omega over half big M plus little m. And it's easy to see.
Cancels
Yeah,
that.
exactly. You're going to So you're going to multiply top and bottom by 2
Yes.
to get rid of that one there. To get rid of that one there.
Wallah, good job, Chris.
Thank you, Mr. Chris.
Okay, so good. Right. Okay, so
قلبي يا قلبي.
This is official.